Today, we're tackling maybe the biggest puzzle in physics, gravity. For a century, we've had the ruling the tiny world of particles and fields with, well, frankly, mind-bending accuracy. But here's the kicker, the real headache. These two giants, they just don't play nice together, fundamentally incompatible. Try to mix them, apply quantum rules to gravity, and boom, you hit a wall, equations break, spitting out infinities, everything goes haywire at the smallest scales, the Planck scale. It's like trying to use software from two different planets on the same computer. Just,
Right.
nope. I've had easier times untangling headphone wires. It's a century-long quest for one theory, quantum gravity, to rule them all.
And that quest has led down some, well, pretty abstract paths. You've probably heard of string theory, particles as vibrating strings.
Right.
Or loop quantum gravity, the idea that space itself is made of tiny, discrete chunks, like pixels.
Yeah.
But there's another angle gaining traction, emergent gravity.
Emergent, meaning?
Meaning gravity isn't fundamental. It's not a basic force like, say, electromagnetism. It emerges from something deeper. Think of it like temperature emerging from the jiggling of atoms or, the wetness of water emerging from individual H2O molecules. Gravity could be like that.
Okay.
Entropic gravity is one example, linking gravity to information, to entropy.
Fascinating. But today, we're diving into something specific, right? This. Quantum Vibrational Universe. QVU. Yeah, QVU. It's a different take on emergent gravity, a specific conceptual model. And our mission today, unpack it, see if its core ideas can actually reproduce something absolutely basic. The inverse square law of gravity. So this deep dive is for you to help you get a handle on this cutting edge, maybe a bit speculative area of physics.
Right. So the QVU starts with some pretty foundational shifts. 4 core ideas, really. First, the big one, primacy of vibration. At rock bottom, the universe is vibration, everything. Not particles in space, but vibrations of space, matter, energy.
Okay, vibration is fundamental. Got it. What's next?
Second, vibration as identity and location. An object's specific vibration, its pattern, intensity, phase, that is the object, and crucially, it defines its location.
So the vibration tells you what it is and where it is.
Exactly. Third, vibrational proximity is space-time proximity. This is key. How similar are two vibrations? That directly tells you how close they are in space-time. More similar means closer.
Huh, okay. And a fourth, gravity itself.
Fourth, gravity is vibrational influence. Massive things like planets are just powerful localized vibrations spreading out spherically. Think ripples. When another smaller object enters that sphere of influence, its own vibration gets nudged, changed, pulled into sync with the stronger source vibration.
Pulled into...
Yes, this vibrational convergence. The vibrations becoming more like is what we see as falling, as gravity. The object trajectory changes because its defining vibration is changing.
Right. And the report we're looking at, its main goal is to check if these ideas, if they actually lead to the inverse square law.
Precisely. The method is check the geometry, link mass to these vibrations somehow, and then propose a physical mechanism for the attraction. See if it holds water mathematically.
All right, the inverse square law. Before we see how QVU handles it, let's just quickly touch on why it pops up everywhere in physics. It's not just gravity, is it?
Not at all. The basic geometry, really. Geometric delusion.
Geometric dilution.
Yeah, imagine something radiating out evenly in all directions from a point in 3D space. As it spreads, it covers the surface of a bigger and bigger sphere, the surface area of that sphere. It grows as the square of the distance, right? A cool 4 for it.
Okay, yeah. Area goes up with distance squared.
So if the total amount of stuff radiating out the flux is constant, its intensity at any point has to decrease. It gets spread thinner over that larger area. Intensity is just total flux divided by area. So intensity drops off as 1 over r squared, inverse square. Double the distance, the intensity is only 1/4 as strong.
And we see that everywhere. Sound in an open space, right? Light from a bulb or star. Like you said, with Mercury and Earth, Mercury is about 3 times closer to the sun, so it gets 9 times the solar intensity. Simple geometry.
Exactly. Radio waves, radiation, it's a consequence of 3D space and something spreading from a point. And it shows up in fundamental forces. Newton's gravity force is proportional to 1 over ln. Coulomb's law for electricity force is proportional to 1 over ln.
Because they act like point sources in 3D space.
Pretty much. Mathematically, for any field like this spreading from a point in n dimensions, it falls off as 1 over r to the power of n1. For us, n3, so it's 1 over r.
So for the QVU, if it just assumes gravity is a spherical vibration from a mass, it kind of gets the inverse square law for free just from geometry.
That's the insight, yes. The 1 r to r dependence isn't the hard part for a theory like this. It's almost baked in by the assumption of spherical radiation.
Ah, okay.
The real challenge, the deeper questions QVU needs to answer are, what is this vibration physically? How do you quantify its intensity? How does mass set the strength? And crucially, what's the physical mechanism? How does this intensity cause attraction? That's the tricky
Well,
part.
so connecting mass to this vibration, how does QVU do that? Is it frequency, amplitude, something else?
It leans heavily on Einstein,
Okay, let's look at this one.
but not just for bombs or power plants, the deep meaning. Mass and energy are the same stuff, interchangeable. Any mass has a huge amount of rest energy locked inside it. In the QVU framework, this rest energy is the fundamental vibration. It's a perspective shift. Mass doesn't generate a vibration. The localized energetic vibration is the mass.
Okay, the vibration is the mass. So how does the energy of a wave, a vibration, relate to its properties?
Standard wave physics tells us the energy a wave carries is proportional to the square of its amplitude.
Amplitude squared.
Right.
Louder sound, brighter light, more energy.
Exactly. Double the amplitude. You quadruple the energy. Frequency is often more like an intrinsic property, but amplitude relates to the energy put in. So QVU connects the dots. Mass is proportional to rest energy, EMCMAR. Rest energy is vibrational energy, QVU hypothesis.
Okay.
Vibrational energy is proportional to amplitude squared, wave physics. Put it together. Mass is proportional to the square of the amplitude of its fundamental vibration, MEVA.
Wow, okay, so gravitational strength is just the amplitude of this vibration. A more massive object is just a higher amplitude vibration.
That's the core idea. It neatly sidesteps asking how mass creates a field. It says the energetic vibration is the mass, is the source of the influence. It's an emergent property of this localized oscillation.
Makes sense. So we have the one-data geometry, we have mass linked to amplitude squared, and the big one. How does this vibration actually attract things? What's the mechanism?
Good question. The reports suggest two physical analogs, two ways to picture it, and they're quite compelling. Analog one is sympathetic resonance and entrainment.
Like tuning forks.
Exactly like tuning forks.
Mhm.
One vibrates, makes another nearby vibrate if it's tuned the same. That's sympathetic resonance. More broadly, it's entrainment. Oscillating systems locking step. Huygens pendulum clocks on the same wall, remember. They'd synchronize through tiny vibrations in the wood. Amazing observation back then.
Right, they influenced each other.
So apply that here. A massive object is a strong, stable oscillator of the source vibration. A smaller object, the test mass, is a weaker oscillator. The source's vibration acts like the wall for the clocks, a medium coupling them. It influences the test mass, causing its vibration to shift, to become more like the source's, to entrain.
And in QVU, vibrations becoming similar means.
It means they get closer in space-time. That's the postulate. Vibrational convergence is space-time convergence. So the test mass isn't pulled. It adjusts its trajectory as its defining vibration synchronizes with the dominant vibration field around it. Attraction as an information-driven synchronization.
Okay, that's one angle. Synchronization, what's the other analog?
Analog 2 is acoustic radiation pressure. Sound waves carry momentum, they can push things. Think acoustic levitation, using intense sound to float small objects.
Right, sound can exert force.
But here's where it gets really interesting. There's something called the secondary Bjerknes force. It's a known effect. You can get a net attractive force between two oscillating things, like bubbles in water, when they're in a sound field. It's real, experimentally verified. A vibrational field causing attraction.
Whoa, okay. Attractive force from vibrations.
Yes. So the QBU analog is the spherical vibration from the source mass is a literal pressure wave in some universal vibrational substrate. It creates pressure gradients. The test mass, also an oscillator, interacts with these gradients. The result, a net force pushing it towards the source, a direct kinetic push or pull from the medium's pressure.
So we have synchronization and we have pressure. Are these competing ideas within QVU?
Not necessarily. The report suggests they might be two sides of the same coin. Complementary.
How so?
Entrainment, the synchronization aspect, could explain why objects attract this tendency towards coherence, information driving it. Radiation pressure, the mechanical aspect, could explain how the force is actually transmitted the physical push via momentum exchange with the medium.
Like the why and the how. Interesting.
It's a kind of dual aspect model. It allows gravity to seem both like a geometric path alteration, like GR, and a force, like Newton. And having the Bjerknes force as a real-world example, that adds physical plausibility.
Okay, this is really coming together. We've got the Burr cohort spreading, masses amplitude squared, and this dual mechanism synchronization and pressure. Can we now formally derive Newton's F equals Gm1 meto 2 r worry?
Yes, we can sketch that out. It relies on putting those three pieces together as premises. Premise 1, source power. The total power P, radiated by the source mass M1, is proportional to its mass, VA M1. More mass, stronger vibration output.
Okay.
Premise 2, geometric spreading. The intensity I of that vibration at distance r follows the inverse square law we discussed. So, intensity is proportional to source mass over distance squared, am1 or I.
Right. Intensity drops with distance squared.
Premise 3, force mechanism. The force F experienced by a test mass, m2, depends on how susceptible it is to the field, which we assume is proportional to its own mass, m2, and the local intensity I of the vibration. So Fm2 or I makes sense. Force depends on the thing being affected and the strength of the field affecting it. Exactly. Now, substitute premise 2 into premise 3. Force is proportional to nup-d-do times something times m1 r rena. Fu m2 m2 white. K1 do m1 at 1r. Combine the constants of proportionality, and you get F1 gm 1 md2 r2, which is precisely Newton's law.
Wow. Okay, that's pretty neat. It decomposes Newton's law into these understandable steps based on vibration. That's quite an achievement for a conceptual model.
It is, and look
Yeah.
at what it implies about g, the gravitational constant.
Right. You mentioned G becomes emergent. What does that mean practically?
In Newton's world, g is just g, a fundamental number we measure. Here in QVU, g isn't fundamental. It bundles up the details of the underlying vibrational physics. You could think of g as reflecting, say, how efficiently mass converts to vibrational power and how strongly that vibration couples to other masses, maybe g conversion to coupling.
So G isn't just a number. It tells a story about the underlying medium and interactions.
Precisely. It gives g physical meaning.
And if G isn't fundamental, could it change? Could it have been different in the early universe, maybe? Could that help with some of those big cosmological mysteries?
That's the tantalizing possibility. If g emerges from these deeper processes, maybe those processes weren't exactly the same billions of years ago. A varying g, well, it opens up whole new ways to think about cosmic expansion, maybe even dark energy or inflation, without needing exotic new stuff. It makes g a dynamic parameter, not just a fixed number.
Okay, deriving Newton's law and giving G a new meaning is significant. But let's be critical. To be a real player, QVU has to go beyond Newton and tackle Einstein's general relativity. Right? That's the real test.
Absolutely. That's the mountain to climb. First, GR's curved spacetime versus QVU's altered trajectory. GR says mass curved spacetime, objects follow geodesics. QVU says massive vibrations alter the medium, causing other vibrations, objects, to change path via entrainment or pressure. Are these mathematically equivalent? Can the properties of QVU's vibrational medium be formally described in a way that matches GR's metric tensor, the thing that defines spacetime geometry? That's a huge mathematical challenge. If yes, QVU might explain why spacetime has the geometry it does.
What about specific GR predictions like gravitational lensing, light bending around stars?
Good point. How does QVU's vibration affect light?
Good.
Photons are massless. Does the vibration change the medium's refractive index somehow? QVU needs a concrete mechanism to match GR's predictions for how much light bends.
And time dilation. Clocks running slower near massive objects. That's confirmed. Vital for GPS even.
Another critical test. QVU might propose that the local vibrational intensity affects the rate of all physical processes, clocks, atomic decay, everything, a kind of universal slowing down and stronger gravitational vibrations. But deriving the exact mathematical formula for time dilation from GR using QVU principles. That's a very tall order.
How does QVU stack up against something like Verlin's entropic gravity? You mentioned that earlier.
They're quite different beasts, fundamentally.
Right.
Entropic gravity is statistical, abstract. It talks about information, entropy, holographic principles. It's more about deriving gravity from thermodynamic-like arguments. QVU is mechanistic vibrations, pressure, resonance. It feels more physical, more intuitive maybe.
Yeah.
But that very concreteness brings its own baggage.
A baggage-like. What are the biggest roadblocks, the unresolved issues for QVU?
Well, the elephant in the room is the medium, the aether problem, basically.
Ah, the idea of a fixed background medium that relativity got rid of.
Exactly. If there's a universal vibrational substrate, does it define a preserved frame of reference? That would contradict special relativity's Lorentz invariance, a cornerstone of modern physics. QVU must define its medium as fully relativistic, dynamic, maybe even quantum itself, not a classical static ether. That is incredibly difficult, maybe its biggest hurdle.
Okay, the medium problem. What else?
Quantization. If everything is vibration, those vibrations must be quantized, like all other fields. Think phonons in a crystal, but for gravity. QVU needs a full quantum field theory for these gravitational phonons, or whatever they are, the graviton equivalent. Then, testable predictions. Critically, QVU needs to predict something different from GR, something we can actually test. tiny deviations from one red right at certain scales, weird effects in gravitational waves.
Hmm.
Without unique, falsifiable predictions, it remains just an interesting idea.
And the big cosmological puzzles, dark matter, dark energy.
Yes, the benchmark for any new gravity theory. Can QVU explain why galaxies rotate too fast, or why the universe's expansion is accelerating without needing invisible matter and energy? That would be a huge win, but it's a massive challenge.
So wrapping this up for you listening, the quantum vibrational universe, it's a really intriguing, intuitive picture of emergent gravity. It successfully rebuilds Newton's inverse square law from simpler ideas, geometry, vibration amplitude for mass, and these plausible attraction mechanisms, and it gives G a whole new potential meaning.
But, and it's a big but, it faces enormous hurdles. Reconciling fully with special and general relativity, especially avoiding that ether trap, developing a proper quantum version, and most importantly, making unique predictions we could actually go out and test. The path forward is heavy on math and theory. Formalizing the framework, proving Lorentz invariance perhaps by linking its vibrational field directly to GR's metric tensor, and then identifying where its predictions might just slightly differ from Einstein's, that's where experimentalists could step in.